now, in order to solve a homogeneous linear differential equation with constant coefficients, we have to do pretty much the same thing as we do for a second order differential equation. The only thing is now that the characteristic equation has degree n. But the idea is that every root of the characteristic equation produces or corresponds to a solution, and all the roots together, they produce n linearly independent solutions, right? So the pattern is that n roots of the characteristic equation, we have n linearly independent solutions. Okay, let me explain how it works. So the ODE here is the fourth derivative, and so this is actually y prime 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 fourth derivative. And so we need to set up the characteristic equation. R to the 4 minus 1 is 0, and the roots are 1 minus 1, I, and minus 1 and minus I. So then the root 1, it gives us e to the t, because this is e to the power 1 times t. Then minus 1 gives us e to the minus t, because this is e to the minus 1 times t. And I and minus I together they give us this pair cosine and sine. And the reason is because I, the real part, is 0, the imaginary part is 1 times I, and here we have e to the power 0 t times cosine 1 t, and to the power 0 t times sine 1 t. It's a bit messy. Okay, so again, every real root of the characteristic equation gives us one exponential function. Every complex root always comes with as a pair of complex conjugate, right? So, and every pair of complex conjugate roots, it gives us two solutions of the differential equation, and they correspond to each other. So one is with cosine and the other one with sine. All right, this is if all the roots have multiplicity 1. So what happens if the multiplicity of a root is more than 1? So if 2, 3, 4. And then basically we need to take the original thing, which is either the exponential function or the combination of exponential trigonometric functions, and then we need to multiply by t squared, and so on until we exhaust the number of solutions. And here is an example, right? So suppose that we have, I came up with this example. It's just because it probably demonstrates all possible cases, right? So this is a differential equation of order 12, and of course I just set it up in advance so that the characteristic equation that r to the power 12 plus 16 r to the power 11 plus 116 r to the power 10 and so on up to minus 4375. So this is actually this, when you factorize this, you're going to get this, right? So r to the 4, r minus 1 cube, and so on, right? So now let us look at this. What this means? It means that r to the 4, then 0 is a root of multiplicity 4. Then r minus 1 cube means that 1 is a root of multiplicity 3, and so on, right? So let us look at them again. So we have 0 is a root of multiplicity 4, Right? So since it has multiplicity 4, it means that it is going to give us 4 linearly independent solutions of the corresponding ODE. And what we need to do, we need to write e to the power 0 times t. That's kind of the one that we start with, which is 1. That's the first one. Then we take t times this, then t squared times it, then t cubed times it, and that's it. So now we can stop because we have found the 4. And we only need the 4 of them, right? So let us look at 1 here. Right? So because of r minus 1 cubed in the characteristic equation, it means that 1 is a root of the characteristic equation and its multiplicity is 3. Right? So since it has multiplicity 3, it means that it is going to produce 3 linearly independent solutions. Right? So then we take this number 1 and raise e to the power 1, so we get e to the power t. And since we have to produce 3 linearly independent solutions, we need to write e to the t, then t, e to the t, then t squared, e to the t, and then we stop because that's all. So these are, now we have 3 solutions, so we do not continue. All right, so then we have minus 7 is the root of multiplicity 1, so which means that it will give us just one solution of the differential equation, which is e to the minus 7t, so that's easy. Okay, and then we also have this part, which is a bit special, so let me pay attention to it, right? So we have this part, r squared plus 6r plus 25. Right, so if we try to write down the corresponding equation, r squared plus 6r plus 25 is 0, then we will get that r is minus 3 plus minus 4i. But since it is squared in the equation, it means that each of these 2 roots has multiplicity 2. Right, so we have 2 roots, and each has multiplicity 2, so which means that together, if they had multiplicity 1, then they would produce 2 linearly independent solutions, but multiplicity 2 means that they have to produce 4 linearly independent solutions. But the idea is the same, so we begin with sine and cosine, so minus 3 goes into the exponent, and 4 goes into the sine and cosine as the frequency. And then since we're supposed to produce 2 of them, so we first write down them themselves, and then we multiply by t. So that's really it. And then we get 4 linearly independent solutions. So 2 are just e to the power minus 3t, and then cosine or sine of 4t, and 2 more, the same thing but multiplied by t. Right? So if instead of a square we had, I don't know, power 10, then we would produce 10 pairs, so 20 linearly independent solutions, but every next one is obtained from the previous one with multiplying by t. All right, I hope it makes sense. So now I will conclude with a little very, very cute problem, right? So first, recall that we have learned that for second order linear differential equations with constant coefficients, right, we made the following observation, that all solutions approach 0 if and only if both coefficients are positive, right? So that's what the previous lecture was dealing with, so then damped oscillations. a very cute problem, and I suggest that you try to think about it, and you may want to share your thoughts in the online discussion. So is it true that all solutions is it true that the same thing holds for order n, right? So in the sense that all solutions approach 0 if and only if all the coefficients are positive, right? True or not? And if it is true,